All right, now we are recording, ready to go. Apologies for the slight delay here. Good. For those of you who have not picked your talks, please do so as soon as possible. Many of you hopefully know that talks and essays will be due, well, simply over the next couple of weeks. This is an opportunity for you to learn about things happening in research right now, or that have been happening over the last few years. We simply can't cover this many different topics here in the lectures, although we are really trying hard to expose you to as much as possible, to as many interesting research questions as possible. And because search-based software engineering is such a broad field, there's so much to explore, really. I just got a question from Willie here. One report for so no, you submit each time one report. So there are 2 rounds. In each round, 1 report and 1 video. So yeah, whenever something is not clear, please just ask. Many of you have already clicked here on the link to pick your papers. What I've noticed yesterday was that, well, even though we have 28 students, only 23 of you had already picked yours. Please pick yours as soon as possible. The advantage is the sooner you have your paper, the sooner you will probably sit down and do some work towards the report, towards the video. Don't take these things, take them seriously, because it does take a good amount of time to prepare a decent report and to prepare a decent video. The last years, we've always seen fantastic videos because students have made the effort to understand technical details, but also to, well, possibly record themselves several times. So make use of this opportunity. You have a couple of weeks to do so. Start early, start early. Each of these items is, if I'm not mistaken, worth 15% for a total of 60%. That's a substantial amount towards your final course mark. Speaking of students in this course, just a kind reminder, on Friday, we have the so-called census date. You might, is Friday? Thursday, sorry, my apologies. So tomorrow is the census date. If you feel like this course is not really for you, you can drop the course and you won't, there won't be any liability for tuition fees for this course. Just for your information. I'm saying this, I'm highlighting this because not every student is aware of this, this opportunity. After this date, you can still withdraw. This is possible. Just at some point, unfortunately, the university will start to charge you. All right. So now let's get back to genetic improvement of software and, well, search-based software engineering in general, of course. You might remember from previous slides, lectures, that programming can be hard. Maybe you've even experienced it yourself. And one of the reasons, well, there are many, many reasons for why programming can be considered to be quite hard. One of them nowadays is that customers, team leads, or they simply one's own, the company, has lots and lots of requirements that might be just very different in nature. In addition, over the last few years, non-functional requirements have become increasingly important. So, of course, you have to, your program has to fit into memory. It has to, it has to make sensible use of the resources. Well, thinking of this now, sensible can mean different things to different people. Maybe you should not hog the CPU. Others might say, you don't really care what's happening on the CPU. You want your task to be completed as quickly as possible. So there are conflicting views here as well, conflicting objectives, and they come from, well, essentially a wide spectrum, a wide range of different possibilities. In addition to all these different functional and non-functional requirements, we also see that, well, nowadays we have to target many, many different software and hardware platforms. We've got lots of different operating systems that potentially behave very differently. We've got all these different objectives that we've already covered, and even the target platforms themselves, the hardware might be very, very different depending on what you're aiming for. For example, just a few minutes ago, I was using the Twitter website on a regular laptop, but also I've used the Twitter app on my phone. So both applications have to make use of the same, well, they have to provide the same service, but they can do so, they can achieve this very, very differently. Even when you focus on, let's say, solely the mobile devices, well, okay, this is a couple of years old, but just to give you an idea, even about 6 years ago, there were hundreds and hundreds and hundreds of devices currently on the market with very different capabilities. Some with multiple cores, some with just a single CPU core, some had graphics accelerators, some had to do this in software, well, software-based, very different amounts of memory that these devices had at disposal. Bandwidths varied widely between 2G and nowadays 5G. So it's an enormous space of devices, of platforms that one has to potentially consider. Well, and it would be a pity if we would have to do this all manually. Luckily, there's some computer support, and potentially genetic improvement software can help here. For those of you who don't remember this, the idea with genetic improvement software is that you take some code that a human has written, and then the computer goes ahead and improves it, customizes it, adjusts it so that it performs better, or well, it gets iteratively improved to match the requirements of maybe customer or a team leader. So what we'll go through today are some, well, let's say success stories here from Adelaide. And most of this work has actually been done here together with or by Mahmoud. Mahmoud has been a PhD student until December last year. He graduated and has now left and is becoming an academic again in his home country. Much of today will revolve around smartphone and smartphone optimization. We here in Adelaide had a 3-year grant on optimizing software on smartphones, and this has not only enabled much research here, this government-funded grant, but also put Adelaide on the map internationally for certain optimization tasks. But also it has resulted in some insights that others have simply not been able to uncover. Yes, sounds like a little bit of boasting here, but I have to say we are a bit proud of what we've been able to achieve here in Adelaide, and this has been recognized by others internationally as well. So if you want to learn more about what we've been doing here in Adelaide, I've linked to a couple of papers here. You can also see them in the on the course website under the recommended reading part. So, yep, I said most of it is about energy optimization on smartphones, a tale of woe and a proof of concept. We focus quite a lot on a proof of concept, and the tale of woe here refers to understanding as much about the problem as possible and documenting challenges that we've encountered, and also trying to come up then with ways to circumnavigate all these challenges. Let's start with the overall motivation. Why were we actually interested in energy optimization? Some of you might have seen this hierarchy of needs from well, the 1970s, I believe. And essentially, the further down you go into this hierarchy, the more fundamental a need becomes. So we all, as humans, we like air, shelter, water, food. This is a very fundamental need that we have. On top, safety and security are nice to have. Social needs are maybe not as critical, but still, well, a nice thing to have. But as we go higher and higher in this hierarchy, we can probably live more and more without actually having them well fulfilled or perfectly fulfilled. Nowadays, maybe in the 2020s or 2000s, this pyramid has potentially changed a little bit, and what can be seen by some as even more important is that we have access to Wi-Fi or to battery, or also a charger. Nowadays, devices are getting better, but if you go back maybe 5 or 10 years ago, well, many people had mobile, battery banks, power banks. Maybe some of you even have power banks. Maybe I can have a quick show of hands or so, or maybe you can leave it in a message in a chat. Do you own a power bank? So these portable batteries with which you can charge a phone, for example. So Vinci, for example, says, yes, I do. So Vinci owns a power bank, and maybe that's because, well, the phone simply doesn't last very long. So then being able to recharge the phone on the go while being out is a very nice thing to have. So Wi-Fi and battery nowadays in the modern age are potentially even more important than, well, okay, this is exaggerating a little bit, of course, but more important than water, food, air, and shelter. And of course, well, we are not the first ones to recognize this. I was at a summer school about 4 years ago in Spain, and there at one of the local tourist traps, you could see this at a restaurant. So this particular restaurant, well, apparently has one of the best vegetarian burgers in the city. But what is advertising also very, very openly is that there's access to Wi-Fi and access to energy, so chargers. So it is very important nowadays. For well, it has been important for us in the past, but it remains very important. Yeah. And this motivates much of our research, but it also motivates, well, it influences how we as humans interact and well, behave with the devices in our hands. I'm saying this because as soon as I see a low battery well, notification on my phone, I'm maybe shocked, maybe you're shocked too. I get angry. What happened again? Is the battery dying? Is which software has been running in the background all the time? Have I been playing Angry Birds or too much or whatever? I don't want to believe it, and essentially I'm running for the next phone charger. And there are many people like this. Well, maybe not as extreme, but there are lots and lots of smartphone users out there. Apparently the current statistics are about 3 billion. So that's 2021 statistics, 3 billion distinct smartphone users on the world. Everybody using the phone, well, several times a month at least, sometimes several times a day, of course. So we all expect to be online over and over again, listen to music, look at the news tweets, share photos, play videos, and so on. But the reality is that, well, phones don't always last that long. They're getting better at it. Some is due to hardware breakthroughs, or so new developments, new chemistries in batteries, but some is also definitely due to the improvements on the software side as well, being more energy aware. And well, we are thinking that, hey, with genetic improvement, we can help out a bit. We can help people use their phones longer by maybe, for example, reconfiguring their apps or rewriting source code. Well, this was our motivation about 5 years ago. We found out that this is not quite as simple. We've come across many, many different challenges over the years. And I'll simply outline quite a large number of these challenges to you over, let's say, the next half an hour or so. Now, of course, here with GI for energy optimization, we are not the first people to do this. And we are also not the first ones who have realized, hey, what can we actually do about energy consumption of software? About, I think, 15 years ago now, there were official, let's say, strategy survey papers on this, where researchers asked programmers, hey, what do you know about energy consumption of software? How do you know what affects actually energy use? And the insights were a bit sobering in the sense that, well, nobody really ever tells the programmers how to optimize for software. It's most certainly nothing that we offer here in this university, and I'm not aware of any courses around the world. Yes, sometimes you have it maybe integrated a little bit into a systems systems design course or some low-level micro-architectural programming course, design course. But we don't have dedicated lectures typically to energy minimization, for example, or memory footprint optimization or bandwidth optimization. Yes, here and there you have them, well, one here, one there, maybe one in the networks course, one somewhere else again. But these are maybe footnotes or just half a lecture or one lecture long. So very rarely we see that a university is actually educating programmers on this. Much of the knowledge here really comes from, well, it's in-house development, and then, well, hearsay and war stories are then passed on from one group to the next one. Together with a colleague, it was in about 2018, we have actually tried to reach out to some of the bigger companies and smaller companies as well here throughout Australia to get a feel for, well, what are companies nowadays doing, because these two papers are quite old. What are companies doing nowadays in order to reduce their energy consumption of their smartphone apps? And well, unfortunately, hardly anyone replied. It turned out that companies didn't really want to share their details on this because it's nowadays a competitive advantage. In a long time ago, people advertised with phones. They would say, my phone lasts 4 hours. The other one would say 4.5 hours. Or nowadays, it's probably more like 13 hours, and the other one says 15 hours. So being able to run the same device for another 10–15% can mean that in the reviews, you get a higher score. And as a consequence, you attract more sales. Good. So we definitely know that there's a demand. People need to know about this. But because people don't know that much, researchers have tried to use, well, some automated ways of improving energy consumption. And among these are, for example, these two papers here, a lot again driven by the colleagues in London, but also by other groups around the world. So there are some first success stories in that direction. Let's think about some of the more technical details, the difficulties of optimizing energy consumption. One of the aspects that you have to consider is, well, when you want to optimize for energy consumption, you have to measure energy consumption in the first place. How do I measure the energy consumption of an app here on this smartphone? It's not that trivial because I cannot, I can break it open, try to find a battery somewhere inside, and then try to maybe disconnect or break certain contacts and put a voltmeter, essentially, or an ampere meter somewhere in between, and then try to measure the energy consumption. But keep in mind that this way I'm measuring the energy consumption of the entire device. So all the little co-processors that are working in parallel, they are active or not active at some point in time. There are lots of other app system processes nowadays that are being executed on this device at the same time. So saying that this particular app needs this much energy is actually not trivial. So this is one problem of essentially assigning credit or consumption to a particular app. In addition, and I've already hinted at this, we would have to break open the devices. And in case of a $1,000 smartphone, not everybody is keen to do this. Sure, about 5 years ago, 10 years ago, many phones had replaceable batteries because batteries were not great and the software was not great. So you had to potentially walk around with a second battery. So then it was possible to have replaceable batteries, and access to the pins where you could then measure power consumption or energy consumption would have been easier. But nowadays, it's quite challenging, really, really challenging, or not even potentially even impossible. Nevertheless, people have tried this. So to do so-called external measurements, which involves cracking open a device. When I talk about internal measurements, then I mean that there are sometimes very, very, very few devices have dedicated tiny little chips integrated into the batteries that do this energy consumption measurement for you at a high accuracy. keep this in mind that we need a very reliable signal back from the battery that tells us, okay, this is the consumption of the entire device. If you don't have a very reasonable system or reliable sensor for this with a high resolution, we can't really say whether variant A is better than variant B. Right? We're going for our search by software engineering, we need to go round and round in circles. We've seen this many times. We modify some code, we evaluate it. If it's not good, we modify it, we evaluate it, we modify it, evaluate it. And every time we evaluate something, it means in our case here for energy management, energy consumption optimization, that we need to run the application on the device. Yeah. So again, yeah, battery, these little battery sensors are very, very rarely integrated. Now, in case you wonder, come on, Marcus, my phone can tell me whether I'm at 100%, 99%, 98% or so. Of course, it can tell you that. But typically, this is just a result of a, sometimes even just a linear mapping of voltage to a number in the range from 0 to 100. And this linear translation does not mean that, well, first, it's very limited in resolution. So you just have 100 or 101 points in terms of consumption. And these 101 points might already be also then, well, if you run an app, they are essentially spread out over maybe 4 or 5 hours when you run your phone at maximum, well, at maximum speed. So a single evaluation can then take a very long time because you want to tell maybe a variant that consumes 43% versus apart from a variant that consumes 44 or 45%. So relying on these single, let's say single digit or 0 decimal places feedback from the operating system here for some devices is just not good enough. Really, really not good enough. Which is also the reason why we did not use Apple's phones here in our research, but we decided to go for Android phones because it allows, in many but not in all cases, access to at least a higher resolved signal, not necessarily a more reliable signal, but one with a higher resolution. Yeah. Now, in addition, what we've done over the years was that we were not only interested in minimizing energy consumption, but also maybe relaxing some of the functional or non-functional requirements, so that effectively would push solutions down into the bottom left corner. And we will see some plots later throughout this lecture, where it's always about pushing solutions into the bottom left corner towards the origin, because we want to minimize energy consumption and minimize the functional requirements. Pairing it with the functional requirement is important because, well, in principle, you can always minimize energy consumption by crashing your phone or by making something go black, the screen goes black, and lots of other things. So if you produce the wrong result, the entirely wrong result, then you can, of course, well, you can often minimize energy consumption very much, but it might not be of interest to your decision maker anymore if your app, if your phone crashes all the time. All right. So what did we actually want to target? What consumes energy on a phone? Here are some measurements for 2 different devices. They are not super new anymore. They're about 5 years old by now. This is a Nexus 9. This is a 9-inch tablet, and a Nexus 6. That's a 6-inch phone. What consumes energy here? It turns out that the screen is a relatively huge consumer of electricity. Here is in the area, well, I won't say it is a relatively huge consumer. Wi-Fi is actually much, much worse. So depending on which device you look at, Wi-Fi can be about 5 times as high as the screen, or 2 times. So let's say somewhere between 2 and 5 times the amount of energy is consumed when transferring information via Wi-Fi, or even for 4G. Compared to, well, just leaving the screen on. So screens are reasonably effective, but Wi-Fi is, yeah, quite an energy consumer. Which probably also explains to you why, when you use the phone for, or maybe an old phone for a very long period of time, and you browse a lot of websites, the devices tend to get quite hot, and this is mostly because of 4G and Wi-Fi downloads. Compared to this, the CPU is actually a relatively small consumer of electricity. Sure, it can be very busy, it can be slow, but compared to the other items there, it's a small energy consumer. But it is an energy consumer nevertheless, and you have got some flexibility there. That's right, not flexibility. You can further optimize this energy consumption of the CPU. The reason why in our research we focus on the CPU is is the following. First, we are software engineers, so we do software. We don't do things that we don't do new screen technology. And the other one is Wi-Fi and 4G apparently have a great potential, but it's also enormously noisy when you measure something. I would almost go as far as to say that the Wi-Fi energy consumption is or depends on the phase of the moon. And maybe, I don't know who else sits in, well, it's definitely dependent on who's in the same room, who's walking around in the room, to which router are you connected, or which access point. Say there are many aspects that you don't have under control. What else is happening on the network, for example? So in principle, again, in summary, Wi-Fi you can potentially save a lot of energy if you optimize for your Wi-Fi connection, but it is also an extremely noisy environment. One more thing I want to briefly highlight about this particular slide here is, these two devices, they are special in the sense that they have very good internal sensors. In particular, we noticed that over experiments that there would be a very good correlation of internal and external measurements. This is important because we did not always want to crack open the phones, and for doing an external measurement, the setup is actually not trivial. It requires you to connect certain leads to maybe a relay here to perform some measurements later on. Some other hardware is actually not shown here on this particular picture. So this overall setup is very error prone. We've had troubles with corroding contacts here. It was not very reliable. So this is an external setup. The internal one simply means that you put the device somewhere on the table, not connected to any charging. It's not charging at the moment, and it's also not connected in general. And then you run your measurements on the device. It is all right. Why is there a relay here put into place? Well, we do have to disconnect essentially the power supply. It turns out the devices, when they think they're connected and they're charging, they run in a different power mode, which completely messes up the internal measurements. You can't rely on them anymore because charge is coming into the battery and the battery thinks, okay, now suddenly I ran all these applications and I've even gained in electricity, in energy. So that's a bit strange. Devices run in different modes, different performance modes, and also the charge of the battery sometimes goes the wrong direction. Good. So there are also already a couple of challenges here, but these are technical challenges that we can relatively easily deal with. Now, this is just a little bit the hardware setup. What did we look at? If we want to maximize or minimize energy consumption, we need to have an application first that we can minimize its energy consumption of. Sure, we thought about targeting an entire operating system. The trouble with this was that compiling the operating system is incredibly time consuming, and it just wouldn't be reasonable. We can't wait an hour or a day every single time we create a variant for the operating system version to be recompiled. This just doesn't work for us. Instead, we looked for apps that were that potentially use a lot of electricity. In particular, we came up with 4 requirements, or had to consider 4 requirements during our search. We wanted open source apps so that we can modify the source code. We were targeting apps that are widely used, so that well, we can motivate our research in the first place. We wanted apps that actually are energy hungry, because if it's just displaying a photo and doesn't do anything else, then what can we potentially optimize there? And lastly, we needed some test cases as well. Test cases or test suite is important. Otherwise, we can't really execute much, or we have to write our own little test script. So this was this was something that we were looking for, and we looked for many hours, and it was actually a surprise back then to see how few apps fulfill all the requirements. Sure, there are many open source Android apps out there. Not many are actually super widely used. For many, it's not clear whether they are actually energy hungry or not. But what's the worst part is very few come with interesting test cases. Now, with interesting, I mean the following. I'll briefly go back here. We are interested in exploring this trade-off between functional requirement and energy consumption. Now, if the functional requirement just says, okay, I can talk to the server or not, or I can display the picture or not, this is very binary. Ideally, we have some gradual trade-off space that we can explore, not just binary 0, 1. Because then there's not potentially not very much that we can optimize. So luckily, we've come across one app, and that's a so-called Rebound library. It's a Facebook app that lets us perform spring animations. And as part of this Rebound app, it does these spring animations, and it does some physics calculations on the inside. So technically, whenever the app is running, whenever this library is used, it's consuming a fair amount of energy because it's calculating how a spring behaves. So you stretch a spring and then you let go. So on one of the programs here on the smartphone, you pull them when you're down. When you let go, it goes bong. So it has these movements, and then at some point it comes to rest. And this is what the Rebound app does. It doesn't do the bong sound, but yeah, it calculates the position of the springs, and you can use these positions then for your menus. And it's used by quite a number of commonly used apps, this library. What we wanted to explore then is, can we maybe make some of these animations by going into the physics calculations? Can we make them less realistic, but this way save a lot of electricity? This was our question. For a user or to user, it might not be that important to see a perfectly simulated spring. Maybe if it's not super realistic, let's say 90% realistic, maybe it can, but it saves maybe 20% electricity at the same time. The user might not care about the 10% disagreement with reality, but might welcome the 20% improvement in energy consumption. And this is the trade-off that we were after. Much following what we've seen last week, the idea of maybe even failing some test cases or deviating from some intended outcomes in order to save electricity. Good. The approach that we've used here was a little bit in contrast to what you've seen last week, parameter tuning. In particular, it's something that's called nowadays deep parameter tuning, because deep X was always something, or has been a hot term for a while. The deep here refers to the fact that we aimed at numbers, parameters that were deep inside the code, and these parameters are normally not exposed to the user, not exposed to anyone who's using the library from the outside. We'll see some source code very soon. And and the idea was maybe you can change these physics calculations in order to save some electricity. The overall process was as follows. We have our original app, and offline we extract the parameters from this app. So again, these numbers that are deep inside the physics calculations that normally nobody would ever touch. So in this way, we modify the original app or library, in our case, to an app prime variant. And this In addition, this app prime would actually take the magic numbers not hard-coded, but it would take them via a config file. Now, this is maybe a little interesting trick for you. This config file, also because you'll be using a similar trick in the assignment 2. This config file has the big advantage that we do not need to recompile the app every single time and redeploy the app to the phone every single time we propose a new configuration, new combination of magic numbers. This is important, again, because compiling an app takes time and deploying an app to the phone takes time. So if every time we have an overlap of 5 minutes, just to update it versus just transferring a small file to the phone, these 5 minutes mean that in an hour, we can maybe do just 12 or definitely fewer than 12 evaluations. Or in a day, it's about, I think, 144 evaluations. This is not very much, given the potentially very, very large search spaces. So that's a little bit of software trick there to speed things up. Once we have this modified app together with a config file on the phone, we can collect statistics via the operating system. We've written a little profiler that lets us collect these statistics. And these statistics then effectively give us our fitness values, these are our metrics. We get, for example, the energy consumption from the operating system. And from the app, we get the deviation from the animations as well. So we have several objectives, several things that we measure along the way. This is all then controlled by an optimizer. The optimizer itself tries to then suggest a new CSV file to the app. The app is run, data is collected. If it's better, then it's considered as the next starting point for the next CSV, and it goes round and round. You have seen this loop many, many times now. So in principle, a very simple system. In practice, it still is not a horribly complex system. Just to briefly show you what this modified source code can look like, comparing this original library with the library prime, the slightly modified one. So this is the screenshot from the original library, and in particular from the Spring.Java class, which was responsible for the physics calculations. In here, we see a number of magic numbers like max delta timesec 0.064, here another one 0.001. And there are about another 20 or so throughout this entire document, essentially the class. We modify this so that all these magic numbers, they get set by a helper script via the CSV file. So here the max delta timesec is now no longer the 0.064, but some value that we feed it from the outside. And the same applies to the others as well. We've done this for Spring.Java, and there were about 20 or so parameters in this class. Some parameters are a bit nonsense, like the 2013 here. That's simply the year of the when a particular functionality was added. Having said this, a domain expert will notice this number right away, but maybe for smaller or other numbers like a 1 or 2 or 3, it's not all 0. It might not always be clear that, hey, these are actually numbers that should not be optimized. So as you can imagine, a 2013 versus a 2015 should have no effect whatsoever on the energy consumption of your app. Nevertheless, an optimization approach like a local search or so does not know this, and it will happily try to increase maybe the 2013 to a 3050. If it happens to observe an improvement, it might even pick this number later again. But the good approaches nowadays, the ones that try to learn a little bit for each number individual, or maybe sometimes for pairs of variables, their relationships, they will learn that, hey, certain numbers are just neutral, or certain variables are neutral, and they don't contribute anything at all to the performance of a particular solution. Good. So this is now the modified app. We're coming briefly to the monitor, the software side again. Yes, in the introductory lectures, I said here for local search, it's maybe 5 lines of code in Python, or simulated annealing might be 10 lines of code. Here, we actually did need a lot more lines of code because we needed to talk, for example, to the so-called fuel gauge chip. So this is highly accurate small chip that allows us to do, well, at least accurate measurements of the energy consumption of the entire device. So we needed quite a framework around this in order to measure energy consumption. So first for the measurement, but also we needed to log information. We actually ended up, and we'll see this later briefly, we ended up logging a lot of information because we had to debug lots of situations. But I'll come to this in a moment. So we collected lots of information. Some of this later we tried to use in a generator, in a model generator, in order to speed up the calculations, to avoid running code on the device. But more on this in a few minutes. So this is maybe the software view at this. Right, where we recorded lots and lots of dimensions. We also noticed that when we start to record too many different aspects, then the energy consumption of just the recording framework itself goes up quite a bit. So you have to be quite aware of this. So as soon as you look at something, you will taint the measurements. So be careful with what you measure. Not that what you're measuring, so your measuring framework actually dominates the actual signal that you're trying to observe. There were lots and lots of noises when doing this kind of research from the system, and that's because, well, a modern smartphone consists of lots of little chips and things. And controllers, they all do their things more or less. Sometimes it's independent of each other, and you as a user, we as researchers in particular, we have no control over them. We can't say, okay, you'll be quiet, you'll be quiet, you'll be quiet. Sure, we can maybe turn off Bluetooth, turn off the Wi-Fi. But maybe some other chip, maybe the GPU does something from time to time, or you never know. There are transitions from high energy states to low energy states that we simply can't control. In addition, the modern Android operating system is very complex. Hundreds and hundreds of processes are running in parallel, and you can't tell them all to be quiet. It doesn't work. You can try to kill some processes, but there will always remain dozens and dozens of processes that you can't kill, and they might get alive or turn live from time to time, do some measurements, do some calculations. And if that happens to be during the time when you're trying to observe your own, let's say the spring calculations, it might quite badly influence what you're seeing. And as a consequence, this is influencing the optimization as well, because you're getting the wrong feedback. Yeah, so 202 processes here in this one case when Mahmoud just looked at the phone once. We've tried to control a few things. So for example, we tried airplane modes. To just get rid of the noise, the incoming noise and outgoing noise due to data transmissions. We changed the CPU governor that sets essentially the CPU core speeds, and we turned the screen off so that we get rid of any noise from the screen, at least to the extent possible. Now, turning the screen off has an interesting effect, and well, actually not doing anything with the phone has an interesting effect after a while the device will go into doze mode or standby mode, during which almost everything sleeps. So all the processes that previously have happily been running from time to time suddenly remain dormant for a while. Then everything gets woken up for a short period, so burst of lots. Everybody computes for a while, and then it gets quiet again. And these windows here, it's not clear how long they are. And if your process happens to do the calculations during one of these either transitions or during the time when nobody is actually doing anything, your measurements will be very badly skewed and noisy. So it's okay, you can't rely on them. Working our way around doze mode has been a challenge, but we've eventually succeeded. So our devices are not going into doze mode again. And as Android got more and more elaborate over the years. So from Android 6 to Android 7, then to Android 8, and more modern ones nowadays. Every time the operating system comes up with newer and more advanced modes, which for us as researchers have made life just increasingly difficult. I mean, overall, it is a nice idea, right? You want the device to save as much electricity as it can. Unfortunately for us, when we wanted to measure energy consumption, this was quite challenging, quite difficult. Another interesting source of noise was that of a device heating up over time. What you see here from left to right is sort of orange shows the battery temperature over time, as we've done some calculations over and over and over again. And you can see that for the same application, the same calculations, we have changed nothing at all. The energy consumption has already also increased over time for the very same app. So there's drift in the system because of battery, because the temperature increases. So the end overall device increases, and it's a fundamental just characteristic of electronic circuits. Temperature goes up, energy consumption goes up. Bad luck. Our approach to this was, well, we had two approaches. One was to put the entire device into a fridge. The trouble with this was that the device didn't like it. Well, it didn't crash, but essentially we ran the same application and the sense energy readings for the same application, depending on the temperature. You see it goes all the way down to about 3-4 degrees, the battery temperature. It was all over the place. So it was not reliable at all. Keep in mind, this is the very same app. We run it over and over again. And the only thing that changes is the outside temperature, well, or the device's temperature as it goes down. So this is not, I'll go back once. Well, here's potentially a nice relationship between these two lines. Sure, it's a bit noisy here on the reading side, but here, as soon as we cooled it down too much, was a different experiment here. It just, everything broke. The entire energy measurements broke. So this was not possible. We thought, okay, maybe we can model it somehow. We can go back to, sorry, I go back 2 slides here. We can measure these, well, take lots of measurements, come up with a nice mathematical relationship between them. But it turns out that for some devices, because there's still so much noise, so deviations from measurement to measurement, sometimes that's trying to come up with a model that is a nice representation. It's just, yeah, it was not possible. We have not succeeded in putting together a model that gives us a reliable energy prediction here. Well, sometimes here underestimated by 10% or 15%. This is not useful then. No. So we tried this based on temperature and some other measurements as well to predict the energy use. So to normalize effectively to compensate for temperature. Yeah, sure, you can always come up with some formulas, but it has been super inaccurate. Yeah. So, and that's a typical problem that we had. So measurements that are, yeah, so predicted measurement and actual energy measurement were not very strongly correlated, unfortunately. So we had to resort to actually running everything on the device. And we propped up this Nexus 9 here onto cardboard boxes and set a fan next to it to control the temperature, at least to some extent. Don't worry, we'll take a short break very soon. So we've set this up and we thought, okay, now we're ready to go. We can do our optimization. It turns out that no, we weren't ready to go. We set the device's speed to 2.3 gigahertz. And what we observed as either the device warmed up or as we just kept calculating more and more and more, the device would get so hot that the temperature governor would then clock down the device. So even though we say stick to 2.3 gigahertz, don't clock down, it would try to save itself from melting and clock down nevertheless to protect the device simply. You know, it's a good idea, right? In principle, the problem is that as a consequence of this clocking down, you also affect other parts of the system. Processes take longer and your energy consumption can go up. So you have readings varying over time. Yeah, if you're not paying attention due to this clocking up and down. So, and we really tried hard to eliminate this to the extent possible. How did we get this under control? Well, instead of going for 2.3 gigahertz, we set our device to 1.4 gigahertz, and then we had a very nice, stable measurement over time with the fan attached out from the outside, of course. So we could run so we would first reach a relatively stable temperature quite quickly. And the measurements that we would take would also be reasonably stable as well. Of this very same app here, you see there's still some noise from time to time, but overall we can handle this. We can, yeah, we are now, we've invested a fair amount of time getting to this point where we can do some optimization. Well, almost. There's one more thing, and then we do some optimization. We had to deal with some of Google's software. And one of the infamous pieces here is the so-called Android debug bridge, which is the piece of software that was responsible, or still is responsible, for talking to the devices. The big trouble was that the device itself was, well, the software itself and the server was a bit unstable. And we had a lot of connection issues. And connection issues in the following sense. Let's say I'm the controller, I'm talking to the phone, and say, okay, here's a new configuration, please run this and give me the numbers back. Okay, phone goes away, does the calculations, give me numbers back. And I say, okay, here's a new configuration, please measure. Okay, phone goes away, measures it, and gives me numbers back. Then I say, oh great, here's another configuration. And the phone doesn't respond anymore. Then try again, here's another configuration. The phone doesn't respond anymore. Here's another configuration. Are you not authorized? Why am I not authorized? It just worked 5 minutes ago. Then the next time I try, okay, now everything's fine. Sure, here are the measurements. Everything comes back. So we needed to use a fair amount of glue code just to keep the system alive. So nothing really, well, optimization related, but just, well, yeah, glue code, frameworks, code that enabled optimization later. Cool. So we've had a lot of fun with this. At this point here, I want to take a short break because it's already 2 o'clock. And then afterwards, we'll see some results of all the trouble that we've gone through. And I'll outline super briefly some current research that's happening here at the university, in this research group. For now, it's 4:06. Let's take a 4-minute break until 10 past. So I'll type this into the chat. Let us continue at 14:10. It's a short break. Everybody can stretch himself or herself for a moment, and we'll continue very soon. All right, it has just turned 10 past, so let's continue. So the first hour was largely about just lots and lots of technical issues that we've come across to enable optimization. In the following, I'll super briefly report on some of the results. So the optimization algorithm that we've used here was a relatively simple genetic algorithm, small population size of just 20. We did a small number of generations, so just 17 generations here, 17 iterations in total. 17 is an unusual number because then something else crashed again, so we couldn't really go much further, but it still was enough for us to observe, well, some optimization. Objectives here have been energy, which we've been preparing now over the last hour, essentially, while keeping as much of the system under control as possible. And we measured accuracy, so accuracy of the animations. We had to consider a few more things in our setup, and one is a timeout. So sometimes we would create animations or calculations. We would configure essentially the system in such a way that it wouldn't finish in time. So we had to consider a 2-minute timeout for each iteration. And also we had to keep in mind the following. As we keep using the device, obviously we are draining the battery. So every now and then we had to recharge the device as well, which then slows down the device, well, the overall optimization as well a bit. Last point here is that well, measuring the energy consumption is obviously important. Unfortunately, you cannot tell the device, okay, start now and finish now with your energy measurement. This is not possible because the sensor itself works at, well, in this case here, at a 4 Hz frequency. This means 4 measurements per second. This has some effects. One of them is the following. If you try to measure something that is shorter than 250 milliseconds in calculation, then well, you simply can't easily measure this because there'll be so much noise that we're measuring along the way. We dealt with this by simply doing calculations, for example, 100 times or 1,000 times, so that we cover, for example, a 10-second, 15-second calculation in total. With these, for example, 10 seconds, we are also starting to see the following effect. Well, by the way, we are trying to not starting to see the effect. We are trying to mitigate the following effect. At 10 seconds, we have, well, 10 times 4 measurements, so 40 measurements. This means we at 10 seconds, so a 10 seconds calculation versus a 10.25 second calculation means that we either have 40 measurements or 41 measurements for the entire experiment. Sometimes this 41th measurement can mean that we're actually increasing the energy consumption by, well, 2.5% here in this case. Yes, 2.5%. So we have to be a little bit careful with how we construct our measurements and how long we run it, run everything for. Technically, the longer we run our experiment for, the better, because then we do not have to worry about this 4 Hz resolution. If, for example, if we push it all the way to a 1-minute calculation, 60 seconds versus 60.25 seconds, of course, the 0.25 seconds are still, well, because we end up with one additional measurement of these 4 Hz, these 4 Hz resolved energy readings, it will automatically mean that we have an increased energy consumption. But in the 1-minute spectrum now, we are quite comfortable while observing differences that are bigger than this under 1% variation as well in energy consumption. So this is another technical aspect that we have to keep in mind. Having said all of this, luckily for you, you don't have these noisy systems. Your assignment 2 will be noise-free. I'm just outlining all these problems to you because you never know what you come across later in the real world, what your customers want. And sometimes there might be lots and lots of dragons hiding inside of your systems at the measurements. And you might accidentally draw wrong conclusions from your measurements. So coming back to this particular experiment, we've run the optimization. Again, we are trying to go for the bottom left corner here, minimize energy consumption, minimize the deviation. This star here is the original configuration, so the one that you can just download from the particular GitHub repository. It has some, well, simply some energy consumption, and it doesn't deviate at all from the original animations, right? These 20 generations, no, not 20, 17 generations at a population of size 20, resulted in some feasible solutions, so some that did not time out. All of them are shown here. And we can see that we did apparently find some that consume about, let's say maybe 10% less energy while still being truthful. So that's not too bad. The energy was reduced by 10%, and the animations still look the same. Oh, that's nice. Interestingly, here in this particular case, we did not find any solutions, and that's just an odd side effect, probably because we couldn't run the optimization long enough. Normally, we would be very keen to see trade-offs here. So maybe some that are even better and consume less, some that consume less electricity and energy, but they are then that deviate. We definitely have some that deviate. For example, this solution here is better in energy consumption, but it's worse in truthfulness to the original animation. This one here is even worse. So normally you would expect more solutions to see at the front. So this one is actually dominating the entire rest of the space. This is a rather unusual outcome from optimization, but part of this is probably because the entire system crashed after 17 generations due to some other reasons. Yeah. We thought, okay, maybe we are consuming less energy, but just because we are taking less time, and to some extent this is true. So we're getting to the same results. So time is here for lots of repetitions of the animation calculations. We are faster, and we consume less energy. Yeah. So sometimes there's this nice strong relationship between the two. You can see the relationship is not perfect, but overall faster solutions consume less energy. Although here you can see some that are faster than the original one, but they actually consume 10% more electricity. So that's a result of our 2016-2017 research. We learned a lot about the smart operating system and how Android works and what doesn't work. And we learned about the internal sensors that sometimes can be super noisy, depending on how we depending on how we treat them. Sometimes they're not very noisy. We learned how to make short measurements. And overall, we established that with internal sensors, you can actually do optimization. Until then, some people would use an entire device battery essentially for one evaluation. So they would load the application that they want to optimize to the device, press a button, wait for 5 hours to get an evaluation back, and then do the same again for another configuration. Of course, this is technically possible, but if you try to evaluate maybe hundreds and hundreds of different configurations, this is just infeasible. Either you need a very, very large phone farm, or you're running out of time simply. So, and we worked hard to enable this, to make this usable in principle for everybody at home, kind of. So this was the 2016-2017 research. We've, of course, pushed this further, a fair bit further. Because of the, so on the first follow-up projects here was the use of models. So we tried to find surrogates, find proxies for energy consumption so that we don't have to deploy even the CSVs to the devices. We didn't want to deal with the connectivity issues. And it turned out that you might remember from just 2 slides ago, because we have this, well, we seem to have this time energy consumption correlation, a decent one at least. It turned out that this time is, well, for applications on phones can be measured in jiffys, which are kind of like the time slices that an application gets. And the good thing is these jiffys you can record without having to disconnect the device. So it's a measurement independent of the energy consumption. Well, it's independent in the sense that the measurement is independent, but it seems to be super strongly related to the actual energy consumption of an application. So here we have variants of some apps of one app, sorry, at different speeds, and you can see nice linear relationships between them, between GFEs, so the number of essentially time slots that an application got, and the energy consumption then of course, in this case, the entire device. So we use this as a proxy, again, with the big advantage that we could run it a lot more quickly. We didn't have to amplify it and run maybe 1,000 repetitions, but we could overall measure the, well, we could push the optimization a lot further than just 17 generations. We also looked at executed lines of code as a proxy, and this also worked reasonably well. Executed lines of code here means that, well, this is something that we can even execute on a regular desktop computer without involving the device at all. So this also worked reasonably well. In hindsight, this means that all the trouble that we've gone through in order to do the on-device measurements has not really been necessary, at least for CPU-bound applications. Of course, as soon as we touch the CPU, as soon as we maybe are interested in transferring data via 3G, 4G, 5G, then these lines of code based models, they will not be particularly helpful anymore because they don't capture other aspects. We have tried, just briefly for your information, to push these models further to capture other components of the smartphones, and we just didn't get very far, unfortunately. It was very, very noisy, and we couldn't, yeah, the models were bad. Yeah. So long story short, CPU-bound applications, yeah, you can have proxies for this. You don't have to go through the trouble of, maybe if you jump, yeah, of setting something up and trying to, well, make the system work for you. Good. So back to the 2017, 2018 research. One other thing that we considered was the following. You might remember that we looked at the table of about 20 numbers in a CSV file. It turns out that when you do a small sensitivity study, and I've mentioned sensitivity studies already last week, where you focus your efforts on particular components, this was really, or this can be really helpful. Here in this case, I know there's a lot happening on this plot. We did the following. We focused in particular our efforts on 5 variables that through some study we noticed, hey, they have written really an effect on energy consumption in these physics calculations. And it turns out that, for example, here, this particular double in line 24, as you increase it, well, to some extent, as you increase it, the energy consumption goes up. But interesting also, when you decrease it, so you take the original value times 0.1, so you decrease it, it actually goes up a little bit as well. When you decrease it further, something breaks, and if you decrease it even further, then something works again. But you have a very small energy consumption compared to the original. So original level is roughly here. Another variable here in row 26. You had the original value, you take it times 10, suddenly the energy consumption drops a lot. You take it times 100, you have an infeasible solution, so something crashes. We take it times 1000, and well, it works again. Other plus here is just an outlier, so it's not an X, but an outlier value here for the box plot. So we have these weird holes also in the relationships. Here, this one is maybe a bit nicer. We have our original value in line 46. As we increase it, energy consumption goes down. As we decrease the number, energy consumption goes up. Well, that's nice. That's a nice relationship here of double 46. And we've got some other relationships here again. So you can vary certain variables within the calculations and nothing bad happens. But as you change it too aggressively, maybe you decrease it here. See, no decrease was possible as quickly gets something bad happens. Or you increase it too much, then something bad happens as well. So we have observed this here. This shows also that it's not a trivial optimization problem. Not at all, because you've got these relationships. Well, the first is non-linear behaviors. You've got these gaps or these holes in this search space as well, where suddenly something becomes infeasible. Having said all this, well, you can build systems around these 5 values. One thing, and this is just for your information briefly, what we did is the following. We've taken these 5 values, and because we noticed that actually the order of magnitude is fairly important, we need to change. We can do changes in orders of magnitude. We actually focused more on optimizing the factors. So having the original number, let's say might have been a 1 in line 46, and we would take the 1 times, for example, 1 times 10 to the 2, so times 100 would be this one here, or this one here is a blue. So this would be the original value times 10 to the 2. This one here would be roughly 10 to the 3, 10 to the 4 as we go up. So we would focus really on the exponents. And this way we could easily go up and down orders of magnitude with our variables, or with our values. Interestingly, so then we press the button, we did our optimization. Again, we are optimizing here towards the bottom left corner, the origin of this particular graph. We have our energy consumption here originally, and we have, slightly adjusted some the deviation from the original animation. And this one is now more like what you would actually imagine an optimization outcome to be like. You have your initial, so the green solution here is the original solution, and then the other solutions become trade-offs of this original solution. In this case, it happened to be, we happened to observe that we could not, I believe, find a solution that was actually better in terms of energy consumption without being worse on in the animations themselves. Interesting outcome by itself, but let's not focus on this too much for now here. So we have no solution that is strictly better in energy while having the same accuracy. But we do have a number of trade-offs, like all these solutions here. They all consume less energy, but they're also worse in terms of accuracy, of animation accuracy. We'll see some animations in a second of how bad this actually looks like. Moreover, as we move here from the left to the right, so we've got several circles here. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9 circles. So 1, 2, 3, lots of here, 7 circles here, red ones, 9 and 10 circles here, and 8 and 9. These are the 8 solutions here, 1, 2, 3, 4, 5, 6, 7, 8, and 9 solutions. And these are the ones along this Pareto front. So these represent the trade-offs. These numbers, they show each column here shows an entire solution. And as we move from left to right, we can see, for example, that this 46 here, as we go from left to right, it suddenly was increased a lot, and then it consumes less energy, less and less energy. I believe it's actually mirrored the other way around. So my apologies, it's the wrong way around here. So this is the one in the corner, and we can save a lot of energy by increasing it a lot and keeping it then at a high level. So it increases, decreases the electricity. In addition, we have other trends here among the other variables. So we have, for example, for green, a rather large modification from the original value by 10 to the 4, and it stays relatively high, but also it decreases maybe ever so slightly from left to right. Other numbers here are the other 3, they stayed largely the same, except for here this major jump of line 26, but overall these all stayed relatively close to the original values. So there seem to be some interesting relationships here. We've got number 46, which is quite dominating the energy consumption as it goes from right to left. But we also have apparently others playing into this relationship as well. And this is just not that straightforward, is obvious anymore with this particular visualization. Right, now you might wonder, what do these weird, these deviating ones actually look like? We've picked one of them. I believe it's one with the highest deviation, one with the highest deviation. And you can see from left to right, as essentially time passes, these are the either speed, velocities, or the positions of the spring endpoint. And to me, as a human user, I would be tempted to say that they don't really look different. Okay, here's this one case where apparently the spring came to a stand still one step too early, but everything else here looks, if I squint a little bit, looks essentially the same. So this also means if I can get to the same result but I go back briefly, I save maybe 20% or 30% of electricity. That's not too bad at all, I would say. Good. So we've looked into this with models once more. We've had interesting side effects. Let me just go to the next one. One of the interesting side effects was that different solutions behave differently on different devices. Okay, and with this I mean the following. We've got here the original, on the left side, the original configuration evolved on the Nexus 9 with Android Marshmallow. This is the distribution. So let's say 30 repetitions on show the distribution of the qualities. And as we go now from, and we have some other solutions here. So we've got another 7 solutions here from left to right. Now, interestingly, we have one solution that stands out a little bit. So we go, sorry, I should also say the following. This one is on the Nexus 9 with Marshmallow. This is on the Nexus 6 with Marshmallow, and this is on the Nexus 6 with Nougat. So different Android versions here on these two. Something interesting happened here. I know you probably just see lots and lots of box plots here. What happens is the following. I'll briefly talk you through this. From left to right, we go on average, let's say down, down, up, maybe equal and up again. Similarly here, from left to right, we go down, down, up, somewhat equal, and then up again, maybe down, up. So these two are consistent. So we look at Nexus 9 Marshmallow, Nexus 6 Marshmallow. If you now change to Nexus 6, but running the newer Nougat, then suddenly the following happens. Instead of going from the original solution to down to row 1, whatever row 1 now means, we go from original to up to row 1. And then it goes down, up, down, up, down, up again. So then, yeah. This shows that we happened to have a solution that to some extent is maybe specialized to Marshmallow, even though we are really just talking about a physics calculation. But apparently somehow it's interacting, it's maybe making calls not as frequently, or it's using the stack slightly differently. It was, well, apparently performing better on, or better than original on Nexus 9 Marshmallow. You see, row 1 is better. And on Nexus 6 Marshmallow, row 1 is better. But when you do the same experiment on a Nexus 6, so you don't run the optimization, but you take the solutions and just execute them, you measure the energy consumption here, it actually goes up. It got worse. And this is quite a, well, we were surprised when we've seen this. We don't have an explanation for it, but it is something that you have to be aware of, that as you transfer solutions from one scenario to another one, you're not guaranteed any performance improvements. Yes, it seems to work reasonably well for the others, maybe with plus minus some smaller effects, but essentially here, row 1 is really standing out. So same configuration across all 3 plots, just on a different target system. Cool. Let me continue a little bit more about, well, the operating system and the troubles that we've had with it. What's happening here on this particular plot is the following. We've used a single application. Rebound again, original configuration. We run it 900 times. Original blue. So we run it, and so on. And then we recharge it, and then we run it again 900 times. Run it. Nothing else. We didn't touch the device. We didn't start any other processes. But there are so many things that we can see here. We see that initially there is apparently a hotter state, and we drop off a cliff, and suddenly energy consumption gets better by about 20–30%. But we didn't do anything, which is interesting. So maybe something inside of the operating system changed. We also see that after the recharging, actually the entire energy consumption of the same app seems lower on average, right? It's all shifted down, but we haven't changed anything, right? Keep this in mind. Haven't restarted the device. We haven't changed anything of the system files. We have just run the same application 900 times. Yep. And also these hot phases, they take different amounts of time. So here it's maybe 40 steps. Here it's about 70 steps or 70 samples, 70 repetitions. And in the end, so this one maybe might look relatively linear to you, but towards the end, whenever the battery is almost empty, it has this weird, strange upwards acceleration in energy consumption. So maybe something in the background thought, oh, let me quickly do some calculations before my battery runs out. You can see this in both cases here. It goes up towards the end again, strangely, very strange. No idea why. Nobody has documented this before. As a consequence, this also means that we have to be incredibly careful with the conclusions that we draw from our energy consumption experiments. Why is that? You say, well, well, you can pick any two data points here pretty much. If I take this one versus this one, well, even though there's a 30% difference, it's the same application. If I use this point versus this point here, well, they seem to be the same, but they were potentially taken or measured under very different circumstances, although we haven't really changed these circumstances. Very rarely we have some outliers here that are just far off for whatever reason. Yep. And this is something that you do not see, I'll go back briefly, when you squash everything into a single, either just a mean, or you squash everything here into a box plot, because you do not see the entire distribution here. This is only something that you can see when you really dive deeper into the individual measurements. So this was the Nexus 6 running Android Nougat. When you compare different Android versions, so this is a different device, these overall trend can even look even differently. So the Motorola G4 initially has these hot states as well. These are slightly different experiments, but let's ignore this for a moment. So I think we also have these hot states and some increase over time, hot states increase over time. When you go from on this very same device, so we're talking about the same thing, the same box, right? And you just load it with a new, different Android version, suddenly it behaves differently. You don't have this initial hot state anymore, but you have some other things popping up from time to time and just badly messing up your experiments. This was the Motorola G4. We also have a Sony XZ here. I know it's very tiny, but you can see these are, even though we are trying really, really hard to keep the device under our control, the operating system still goes through several states. So we are just, in this case, you might see the 3 bands. These are not 3 different experiments. It's just that sometimes the device thought, okay, and not the device thought, the app used this much electricity, then this much, then this much. So the device itself went through different discrete states, or it attained different states, but we had no way of controlling this. And here, down here in the bottommost row, it's maybe something like 7 or 8 different states. This is just completely useless for our kind of optimizations we are trying to run. Ideally, we have something that is as flat and nice as here in the Nexus 9. Nexus 6 was also okay, so Nexus 6 and Nexus 9 were our favorites later for optimization. There's a lot else happening here on these slides. Just to let you know, the purpose of this particular research was in 2018, 2019 to determine which devices do we actually want to use for our optimization experiments. And it was really because we had these, when I go back, we have observed these weird things that we can't control them, these hot states initially and these drifts in sensor noise. So we still have an increase over time, right? We didn't change anything. So we needed to identify some of devices that are not usable. And in our case, the Sony XZ just was, was not good. The Moto G4 was also reasonably bad for our purposes, and we decided not to use it later, at least not very much anymore. Something else that you can see on the slides, and I won't bore you with too many details, are these bars here. What these bars are, they are essentially derivations from these noisy experiments. where we're trying to provide recommendations to a programmer or to a software engineer to say, here, if your performance difference is, let's say, 1% between different, or here, in this case, 2.5% between two different variants, you need to perform at least, let's say, 20 repetitions in order to have a reasonably high confidence, like do a Wilcox rank sum test, and at 20 samples, you can actually tell them apart at a confidence level of 0.01. Sorry, of 0.001, 0.001, yes. If you're happy with just a 5% confidence level for your Wilcox rank sum test, you need maybe 5 to 10 samples. So the research question, the gap that this slide here was, or that this research was addressing, was the following. We know that measurements are noisy, but nobody has ever told anyone, hey, you need to run your experiment for 1 minute or for 5 minutes. So that is one evaluation. You would just do something and hope that the right thing comes out. Maybe 20 seconds, maybe 5 seconds, whatever you think was reasonable. But they did not account at all for the amount of noise in the system and the different states. And this is what we tried to derive here with this particular paper. It's a 2019 CSC paper, if you want to learn more about it. It has all these nice plots in there, and it explains how to arrive at these bars. What the bars also reflect is the higher the bars are, the more experiments, the more repetitions we need to run, the longer we need to run them. And for example, here in this case, we can see that we need to run the experiments for a really long time because there's so much noise in the system and because the difference between the two program variants is actually very small. So it's a 2.5% difference. We have a lot of noise in the system. So we need to run our experiments many, many times for long periods of time in order to make good, well, reliable statements. There's still even noise across the bars, but let's ignore this. As the difference between the two variants becomes bigger, I say 20% even, then we can get away with a relatively small sample size. But well, even sometimes here in the case of the Sony, we would have a 20% performance gap between two applications, but the noise would be so enormous that it was essentially unfeasible, and the bars are very high. And if the gap is just, say, 5 or 2%, 2.5%, we would have to run so many repetitions of our software to get a decent signal out of this that it's just, yeah, it's no good for us. So long story short here, as soon as you're working with something that is noisy, you enter a world of pain, unfortunately. But there are ways around this. One more thing that we considered then last year was the following. Well, let's assume we do all these careful experiments. We run like we run our evaluations long enough, but we still end up with these, for the very same application, these distributions, right? One being shifted lower than the other. You've seen this one about 3-4 slides ago. Just a bit squashed here now. So what we don't want to happen is that we have two variants and we say, hey, these two are different, when they are not. So yeah, to deal with this problem of maybe restarted devices or recharge devices, we varied it a little bit from experiment to experiment. We have to consider all this noise in the system. The system apparently does, the operating system does things. We have to censor noise as well. So, and we could not perfectly explain where all this noise has come from. And it turns out that some of this noise comes from just, well, it's induced by the operating system. It does things between restarts. You might initially think that restarting a device is a good idea because the device potentially forgets about all the stuff that's been going on and that's been clogging up the memory, and maybe processes have been started and starting and so on. This is, well, it turns out that there are different, as you restart the device over and over and over again, you actually, the system goes into different states and you have no control over this whatsoever. I know this is a bit small here, but I'll still talk you super briefly through this. From left to right, you might be able to see different colors. There's a dark blue here, a light gray, some orange, some yellow, some two greens again, and so on, different colors. And all these blobs here, these little clouds, whenever they have the same color, they mean they belong to the same restart. So these are all same measurements, same experiment over and over and over and over again. And as you go from one experiment to the next one, 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 every time the device, well, not every time it entered a different state, but here we have apparently one low state that's attained maybe 4 or 5 times. Then there's a medium state, and there's definitely a high state, and there's maybe even one extra outstanding state here. And these are the number of active processes running in the background. Sometimes we have 100 processes, sometimes we have 200 processes, then we have 150, then 100, then 200, then maybe 150 again, then 100, 100, then 250, and then 200 and 100 again. And this, you have no control over this, unfortunately. And because all the stuff is running in the background, it also affects your readings. And this can then result in the entire thing being shifted up or down, which then also means that you have to, well, adjust your the interpretation of your results. Lots of other things can happen along the way. Your memory consumption might change. For example, we have, and this is maybe an interesting thing to highlight. From left to right here, we have maybe 100 processes, 200 processes, 150, and 100. Here, the system memory use is always very roughly the same. Something happened here at the green one. So it has the same number of processes as the gray one here, but it uses about 50 or 100 megabytes more. Why is that? Why does the same system, well, even though we haven't restarted it, it wasn't allowed to talk to anyone via the internet, why are we suddenly using more RAM? Or why is the system using more RAM? And we've got no idea why that is the case. But it is potentially affecting the energy consumption measurements, or it could be affecting other measurements as well that you're doing. Yeah. There are other things that we've observed along the way. Yeah, lots of fun here, and all these things can affect how you, can affect your ability of telling two variants apart. Our approach then was the following. Let's say our optimization results in 3 different variants. And what we would do in order to mitigate all these different effects and to average as much out as possible is the following. We do run, so we have 3 solutions, A, B, and C. We do the following. We run ABC, 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 ABC. And then we restart the device, recharge and restart. And then we rotate through ones, because sometimes we have the hot states in the beginning. We do BC, ABC, 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 and then we restart and recharge, and then we go C, ABC, 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 to average out these effects. It turns out that through this averaging out, for example, the number of active processes in the background is now a lot more stable across all the different variants. So we've through this restarting and this rotation, we've established this. Well, we have a scheme now that lets us compare the solutions now fairly. And with fairly, I mean they all have experienced some states with lots of active processes, some high memory use, and so on. And the hope is that by averaging out all these effects here, by exposing each variant now to these different conditions, we can more reliably say that, okay, we do the experiments, we've compared them fairly, and if we still see a difference between them, then it's actually a real difference, and not like here, a fake difference, which was the consequence of, just the system doing something in parallel, but we are still having the same system variance here. So that was really important. We really don't want, we want to make truthful statements, but this also means that we have to make quite an effort in order to arrive at a system, at a framework, a logical framework that lets us compare solutions, configurations when we have so much noise in our system. Okay, I've been complaining for a long time now, for pretty much the last 1.5 hours. This all is to show you that there can be lots of challenges when your system is not deterministic. You don't have this problem, for example, with bug fixing, typically at least. You fix a bug, it's gone. you have a branch coverage of 66%. You run it tomorrow, you still have a branch coverage of 66%. If you don't change anything, it doesn't magically jump down to 64%, and next time it's a 78% again. So, which we apparently are observing here in our measurements. So if you're working in a noise-free environment, your life is much, much easier than, well, in this case, Mahmoud's life, who, yeah, well, he managed to achieve a lot, but it was not what we had initially intended. It was, yeah, much more painful, much more insightful probably as well, because it was not straightforward, but definitely not as straightforward as we had initially envisioned. So this concludes the energy optimization part of the day. Super briefly, I want to tell you what else is happening in the research group. I'm working with quite a few people, and I'll just super briefly run you through what's happening in this greater space of code optimization, Sofware software engineering. So, for example, with my colleague Brad Alexander, I've been co-developing with colleagues in London a tool called Gin, and Gin is the tool that you will be using for the third assignment. Not the version from the website, but a slightly older version, which is a little easier to use or simpler to use. We needed this tool because everybody who does genetic improvement of software creates his or her own tool. Bill Langton has his tool chain for C and C++, and for CUDA code, but it's not publicly available. Other researchers do other code for Python. We've done our code for Java and so on, but it's not really shared, unfortunately. So the idea behind Gin is really that we have systems that can be used by everybody in the community, and that can be extended by other people in the community, adjusted as well. Yep. So that's a tool. Mahmoud has not used the tool. He has done much of this parameter tuning using lots and lots of phones. Through all these phones, we've involved, for example, lots of master's students in our projects. They've been responsible for example, setting up such phone farms or doing other measurements. Yeah, there's always scope for capstone projects here in our work. Together with my colleague Yuval in the security space, we've used, or we are still using, genetic improvement on local search, at least to reduce power-based information leaks in assembly code as it runs on microarchitectures, also microprocessors. So you would have, for example, some decryption code, decrypting messages. You would not listen to what's happening on the memory, but you would just observe the power consumption of the processor along the way. And it turns out that from the power consumption of code that's being executed on the CPU, you can deduce what the key is that's being used. And as a consequence, just by listening to what the processor does, essentially, or on the energy consumption side, you can get access to messages that you shouldn't be getting. And we've used genetic improvement in order to modify code so that the leaks get smaller and smaller and essentially disappear, but depending on the depending on the amount of effort that you make. So there's a short video, if in case you want to watch that later, you can definitely do this. It'll be in the updated slides. They are not uploaded online, not uploaded just yet, but they will be uploaded after this lecture. Supun is another PhD student. He's been working together with Christoph and also Yuval and myself on fuzz testing. The idea is to create test cases that crash programs, and in particular for libraries, this hasn't really been done very much recently. So Supun is also looking there at optimization in a slightly security, but also testing space. We have another PhD student, Mahfouz. He's looking at a very different software engineering problem that is looking at software artifacts, in particular the activities within a repository. This can be helpful, for example, in when the following happens: you go on holidays for 2 weeks, you come back and you wonder, okay, what has been going on in the repository in your company, or in the particular project repository. It would be good if we had a way to automatically summarize the activities in there, but well, we can always summarize by just giving you the raw output or the raw activities, but ideally really point out the important aspects so that you don't have to work your way through maybe 50 commits, 3 pull requests and lots of other things to get the essence of, okay, what's important now to you. And we've been working towards an automated system that creates meaningful summaries of maybe 5 or 10 sentences from the activities in a repository. So if you want to learn more, there's also a paper linked here. With Brittany, who started off with, well, actually it was an honors project, not master's, and who's now doing her PhD with us, we looked at code snippets, so code taken from Stack Overflow, for example, and we are incorporating this into other systems as well, for example, to simply provide features, functionality. So there are more projects along these lines. For example, with Refat, we are looking at the use of static checkers to speed up genetic improvement. That's where with Sherlock, who's working in New Zealand. So in case some of this work interests you, we can always provide lots and lots of different directions, whether it goes into the security space, whether it's the more mining repository space. Maybe you want to get your hands dirty with some hardware. We can definitely accommodate this, or your preferences there. Cool. And so it's a hot area. Some projects are funded by the government, and it was just last week that well, it's for an unlisted PhD student here, that we got money from Google in order to optimize some of their cryptographic code. So yeah, we have got funded projects with industry, funded projects with the government as well, that enables much of this research. So it's a very, very hot area. Yes, maybe not as hot as some of the deep learning stuff that's currently happening, but definitely something that attracts attention of companies and the governments as well. Cool. Having said all of this, it's now almost 3 o'clock. Yeah, this concludes today's session. My apologies that it says 2020 in the corner. I've definitely updated the slides a little bit, so that's a 2021 edition. If you have any questions, please ask now. I'll stay here for another 1 or 2 minutes. Yeah, and if you don't have any questions, thanks for coming here today. I will send very soon, probably tomorrow, an email with information on what's going to happen next week. Cool. All right, as I said, I'll stay here for a minute, so yeah. So here, I'll just briefly update the number. Then let me do the following, given that there are no questions at the moment. Yuncheng and Rui, I'll close the meeting and I'll upload the updated slides now. If you have any questions, just contact me via the course forum, or well, just ask on the course forum as well, of course. All right. Bye-bye.